I'm part of the GeoLab project through TU Delft in the Netherlands. And what I'm going to present you today is quite a nice collection of all the recent advancements that have been done in physical modeling that will enable the next generation of measurements and the next generation of models that we will see in the coming years. And they are of particular importance if we see this need to address the current state of the critical infrastructure. I probably read the same report as Lee showed you this morning or early today on the EU priority sectors. So the EU has identified through all the recent context that the energy sector, the digital infrastructure, transport, and space sectors are of utmost importance. And we believe that physical modeling can provide an insight into how to protect and ensure the proper behavior and proper expectancy of these sectors through the complex soil environment and structure interaction. And that can be achieved by different methodologies. And one of them that you might see quite frequently here is centrifuge modeling. So just for those who are not too familiar with centrifuge modeling goes basically on this principle. You have field scale stresses, and we know that the soil behavior is not linear. So when we test a small specimen, we want that the stresses on it reflect that of the prototype or the field scale. There are different ways to achieve that, and one of the ways we use in a boundary value problem is to put it in a centrifuge. By putting it in the centrifuge and spinning around on a given axis, we exert on the soil a centrifugal acceleration. That centrifugal acceleration allows us to increase the self-weight of the material and therefore increase the stresses acting on it. So with that in mind, the following instrumentation needs to be small or relatively small in order to fit within these models, but capable enough of providing information on stresses, deformations, and other characteristics of the processes under study. I will go through different kinds or different effects of that might interfere with the critical infrastructure. And the first of those is this erosion and scoring due to waves. There are different models or model containers that will allow to study that. And one of them is here, and probably if you say tomorrow, you will see it. And is this very nice miniaturized tsunami generator. So this container, what consists is that has two separate chambers, and you can build a structure, for example, here drawn as an embankment, and discharge a wave or a sudden release of water with a given height and explore what is the effect of the impact of that wave over the embankment. And by doing that and getting right the stresses on the model, you are able to tell if that critical infrastructure will sustain the action of those stresses. There are other approaches as well, as for example, the study of internal erosion or erosion on sand layers. And this is a method that is supposed to be possible to put it in a ship or put it in a work site and just extract directly the sand cores on a seabed or the sand cores near a dike and start studying the effect of a flow going around or over the surface of an erodible layer. There are other approaches that can be used in small scale models. Here we are not in a centrifuge, but we are in a reduced channel. And by placing these little tracers next to the yellow structures, we are able to monitor what are the displacements in a three-dimensional fashion. So this is a stereophotography in a small scale. But that same or similar approach can be used for a field scale, where the use of different tools, like the ones shown earlier before by in the first round of presentations, allow us to tell with some level of accuracy whether or not displacement have been occurred in the field or in the experiment, and whether or not those displacements are induced by the action of a river, the action of weather, or any different action that might lead that infrastructure to a critical state or to a failure state. Other types of load that are of utmost importance for the whole life scenarios of the current infrastructure is what is the effect of these environmental loads on acting on a wind turbine or acting on a foundation system. Those loads have this characteristic that they are cyclic. They go and come, and they're not very intense, but just the cyclic action of these loads might lead the infrastructure to fail. So there are different alternatives for studying these type of loading systems in a centrifuge model, like for example, the ones that are developed in NAND, where you have a different set of actuators and you can simulate the whole behavior from installation to cyclic loading in a simple and single test. There is the option to explore what is the effect of driving, therefore allowing for the perfectioning or the improvement of the current driving techniques. So if you just walk by getting to this building, you notice that there are driving some piles next to it. And those piles are relatively traditional, and we have been building with those piles quite some time, but certainly there is some room for improvement. And here we have the chance to address those improvements and see which characteristics can be better designed. There are other capabilities, for example, studying screw piles or helical piles that are quite common in offshore industry. And here, what people is interested is how to optimize the driving methods so you ensure that they are very well placed inside and can sustain the loading. Of course, loading of these environmental actions is never one directional. You can have loading that goes in different directions and so on. You are interested in understanding how a collection of piles connected together can behave if the load is applied to a certain angle. And that can be done in different ways. One of, for example, is this gear system, where you have this kind of a Swiss clock, being in Switzerland, where each of the gears are rotating and you change the masses along each of the gears. And by changing them, you can control the sinusoidal load with a great precision. So this is a beautiful machine that can allow to test the orientation of loads with a great control and great control both in the intensity. As I said before, here the purpose is not to reach failure just by a single load, but the purpose is to explore what is the effect of cyclic loading in the degradation of the shear behavior of the soil or the degradation of the soil structure interaction. Another type of models that can be developed for studying the interaction of loads to infrastructures is, for example, this wave tank. This wave tank is something similar that you will find in hydraulic engineering. And at the end, we are all engineers, so we take inspiration from good examples in other areas. And what you see here is one plunger that moves sideways, and by that motion, it pushes water sideways. And therefore, you can install a given infrastructure. You can install a wall, a quay wall, or you can install a foundation over an erodible sand layer and explore what is the effect of this waving mechanism on the soil fluid structure interaction. And on top of that, you have now the access to these fiberglass sensors. These fiberglass sensors are quite some of the state of the art on it, and we are still probably exploring a part of what you can achieve with them. And basically what they are able to tell us is that just by sending light across a fiber optic, like the same you probably have in your house for receiving internet, you can tell if something had happened on the way of that length, and if something happened that generates an accumulation of the reflected light. If you process or you interpret that behavior properly, you then can identify the proper location for those strains. And if you understand or you assume some mechanical behavior in your structural element, you can even tell the forces acting on it. So these fiber optics are used for several purposes, for displacements, for pressures, and certainly more to come in the near future. Another example I want to add here is the study of submarine landslides in the centrifuge or outside the centrifuge. And here what you see is a work we have performed in my previous position at the Universidad de los Andes, where we were interested not just in the fact that how submarine landslides can evolve, but also how far they will reach. And here you see a very simple experiment in comparison with a numerical simulation where you have a submarine wedge, and that wedge is suddenly released. The release of that wedge eventually leads to the flow of grains and the flow of fluid around it. And an interesting observation we got here is that it's not only the grains that can impact our infrastructure, but also the fluid that is expelled out. I want to call your attention to the red area on the simulation. You notice that the fluid gets apart or away from the landslide, and that fluid is dragging any infrastructure that will face next to it. So it is not only the run-up distance of the submarine landslide that we should be worried about, it's also the potentiality of the fluid that is expelled or pushed by this landslide. Another type of interaction that is of most interest is these dry and wet cycles and drought. With climate change, we are pretty aware that these can become more intense. And therefore, there are alternatives for studying them. One of those alternatives is, for example, in preparing samples that are more representative to what we expect to find in the field. And an example that probably Luke will tell with more detail later is this one of 3D printed soil samples. So 3D printed has came to the point that we can even prepare heterogeneous samples for centrifuge modeling and address the role of that heterogeneity in the overall soil structure interaction. Other alternatives are this work for preparing expansive clays, where they, with a cheese grater, they prepare these very unstructured clay stripes that eventually are compressed, and you will expect to have a very random orientation of voids within the soil. That random orientation of voids certainly has a difference in the way the soil interacts with a given structure and can tell us with more detail what we are probably missing by doing very uniform soil samples. Other aspects that can be explored are, for example, these ones of collapsible soils or peat, where it is not a sand or clay of the most typical materials we test in the centrifuge, but that it has this internal structure that can certainly vary what we expect to have in the behavior. For example, in the case of peat, one of the works we are ongoing at TU Delft is to study the effect of gas or the generation of gas in these pits and how they may interact or may lead a certain slope towards failure. And last but not least, we have these opportunities to explore the effects of climate directly on the centrifuge model. This is quite a challenge and something that requires a lot of instrumentation. What you see here is something we like to call a climate chamber for centrifuge model. And what you will do is that inside this climate chamber, you will place your centrifuge model, and you will be able to control air temperature, relative humidity, radiation, wind, rainfall, or even relative humidity within the soil. And by controlling all those, you can do cycles that reflect a potential drought season or a very intense rainfall season. And for example, as is shown in this figure, study the behavior of an embankment, and something that is very important if you think of countries that are below sea level. Other interesting options that are available now or are under development for new sensing methods are, for example, the use of these shortwave infrared images. Here, the basic principle of this technique that is being developed in Barcelona is that just by looking at the range of from infrared to ultraviolet, you can get extra information that is just away from the visible light range. So you use special cameras that can have this infrared range, and by noticing how the water content changes, you can link that to the saturation degree. And this is a very important in small scale models, because imagine we have to place a sensor that can act as an anchor to the soil. Therefore, we might be misleadingly seeing that the whole system is relatively stable, while it's just the cable that is reinforcing it. So by doing this indirect measurement, we avoid to put sensors inside the model, and we have a more rich set of information on the saturation along the soil and along different water soil weighting conditions. Another alternative is this fiber optic again. But in this case, I want to catch your attention to the size of these sensors. So you have here a pin, but the sensors are way smaller. And what you have here is a similar approach to a diaphragm. What you will have is a flexible membrane that deforms. At the deformation of that membrane will push an oil inside a chamber. And that oil pushes eventually a fiber optic. The pressure acted on that fiber optic end will be translated to a certain pressure. And therefore, you start having a more direct measurement of what really is the pressure within the soil voids. And that is something that is very promising and certainly an ongoing work. And now getting towards the end, I want to present you some of the works that have been done for freeze thaw of permafrost. We know that now we are losing more and more of the permafrost, and that leads to conditions that we were not expected before. So for example, what is the effect of having this permafrost defrosting or loss in a slope stability problem? Here, these experiments are done in lab scale, so not really inside the centrifuge. However, there has been some works in the centrifuge, but just because it's easier to keep a soil sample cooled in a lab container. And what you expect to see here is just what is the effect of freezing and thawing on a simple slope stability problem? Or for example, when you have a gas pipeline, there has been some works that show that these cycles would lead the pipeline to pop on the surface and certainly disrupt or cause some serious deflections on the pipeline. Other approaches to this are more towards the field, and NGA has done very nice work on this, and is to monitor directly what is the effect of these freezing and thawing cycles on existing infrastructure or on existing slopes. And by doing these field scale experiments, gather enough information that could be used to develop or to design new mitigation systems. Now getting towards the end, the final one I want to show you, or that was collected in this report, is the effect of aging and fatigue on critical infrastructure. So aging and fatigue is quite an important scenario that we need to address. If you now consider that this boom of infrastructure that was built during the 50s and the 60s is already approaching its life expectancy, but probably that life expectancy can be extended. So aging in the soil is very important because soil might gain some strength or might lose it. So we need to understand what is the potential paths for each given material and for each given soil structure interaction. For that purpose, there are some relatively large infrastructures that can help in addressing that. For example, the large-scale triaxial apparatus at the University of Maribor, who is also part of this project, or the track box in SEDEX in Madrid, also part of this project. In both cases, what you have is large containers where you can control the stress conditions acting on a soil sample or on a soil layer and start loading the system with a repetitive action and through a long series of cycles, something that goes in the range of 10,000 cycles or even 100,000 cycles, and understand which are the potential deformations or changes in the soil behavior. So basically, that is what was considered in the report that Sam told you a moment ago. And that was the presentation. Thank you for your attention.
Miguel, thanks very much. So next up, we have Luke Torrell, I believe. We do have a moment for a quick question. If anybody has a burning question they'd like to ask Miguel.
Oh, thank you.
As we transition over to the next presentation. Can't see any hands raised. It's very comprehensive.
Oh, there was one.
Oh, no, there's one yet. Samson.
Thank you for can you hear me?
Yeah.
Thank you for a very nice presentation. It's nice that you're looking on the submarine slides. My question is, you showed that the water ahead of the slide we have to think about that. That's important. But are you also looking on the soil itself, how it is propagating and hydroplaning, its propagation and everything, or
Yep.
just yeah?
Exactly. So the runout distance is definitely a function of the soil. And there, what we have been studying is the effect of grain size distribution, but all these cases into a granular case. So no viscosity, no clays so far. And in those cases, the moment you start having a wider range of grain sizes, you reduce the porosity, and therefore the expelled water gets stronger and farther. So that is something we can address. And certainly the grain size distribution do have an effect on the kinematics of the process, but not on the runout. So if you assume you keep the same material, but just change the sizes, what you will expect to have is probably some faster flows when you have just single size grains. When you have more grains, the flow will be slower, but at the end, it will be the same runout. Thank you.
Okay, thank you very much.
Okay.